Hello everyone, and welcome back to our session on effective network inference. As I hinted at in our last short video, it should really be obvious by now to you that transfer entropy is a very natural fit for us to use for effective network inference here. Clearly, it's giving us a measure of how to model directed relationships and to do so in a nonlinear way. It really aligns very well with what we expect from an approach for inferring effective network structure. So how can we actually use it? Let's have a look at what we call the basic approach in our chapter in the book below. This was a way of characterizing the earliest approaches to use transfer entropy for effective network inference. The idea here is to first of all measure the pairwise transfer entropy between all pairs of variables in the system, and then to simply threshold those transfer entropy values to select connections for the network. We can try this very quickly in JIDT. Let's go and start the transfer entropy auto analyzer, and we'll make sure that we tick the all pairs checkbox. Let's have a look at that. Okay, so here we are in our JIDT distribution. We'll start the auto analyzer by double clicking the jar file as usual. We'll start the transfer entropy auto analyzer. Now what we'll do is I'll leave the KSG estimator there. We're going to come in and pick a data file. I'm going to grab 4 columns with a one-step dependence between them. And importantly, as directed, we're going to click all pairs here. Okay, so we get an all pairs analysis. Apart from that, I'm just going to leave all the properties as they are for the moment. Instead of computing the result, because we've got a lot of calculations coming here, I'm just going to generate some code for us. And let's have a look at the MATLAB code. What we can see here is that by clicking the all pairs button, we now get for loops generated here. For all sources and for all targets, we get a transfer entropy measurement between them. Okay? And we can go over and run this MATLAB code and see what gets produced. Let's do that right now. In fact, I'm going to do this in Octave. We'll go to where the auto analyzer produced code for us, which is this generated calculator MATLAB script here in the demos auto analyzer directory. So I'll open up Octave, and now let's just run it. Okay, when we do that, we can see we get transfer entropy measured between each column or variable in the data, and we get those values right here. The slides went on to ask, what is the first issue that we encounter? Okay, we saw the transfer entropy measurement for all the pairs in the data. And we talked in this basic method about then thresholding these. So what's probably the obvious issue is, what should the threshold be? What should the threshold be? In this example, it's kind of roughly clear that we could probably pick out this guy and this guy as where our connection should probably be. So we probably want a threshold that separates these two from the rest because they stand out quite a lot. So we could make the threshold here maybe 0.1 nats. But other data sets are not going to be as clear as this one. So what should we choose for the threshold? How can we make a principled choice of that? Again, the answer is probably fairly obvious to you given what we've talked about in our previous sessions. Let's then talk about the next step of analysis, what we call the standard approach in the book chapter in the Bossemeyer book, where we deal with this question of how to principally choose a threshold. Here we change the algorithm gets changed. Firstly, we do measure the pairwise transfer entropy between all pairs, but then for each source target pair, what we do is obtain the p-value for measuring the observed transfer entropy under the null distribution. And as we discussed during our previous session on information transfer, comparing the measurement of transfer entropy to the distribution we would get under the null hypothesis that there's no source-target relationship, that gives us a really good way of checking if there's a statistically significant relationship, directed relationship between the source and target. So what we're suggesting here is that using the p-value gives us a very rigorously determined threshold that we can use for each source-target pair. Okay, so we can use those p-values, we can threshold those p-values then to select the connections for the network. If we select a threshold of 0.05, for example, then our threshold becomes the level below, and the level, above which we are determining that there is a statistically significant directed relationship between the source and target pair, with a 5% chance of picking up links spuriously that don't really have that relationship. So as I said, this is a much more principled approach. We are statistically deriving the threshold in a rigorous way. It's robust and it's suitable for small data sets. This takes the guesswork out of what the threshold should be and determines it in a rigorous way. We can try this in JIDT fairly easily. Let's go back to our auto analyzer, and this time, as well as ticking the all pairs checkbox, we're going to tick the add statistical significance checkbox. What this will do is keep the same loops that we had before, but now provide some p-values that we can test more rigorously than just guessing what the threshold should be. Okay, so let's pull up our auto analyzer again, and this time I'll click the add statistical significance checkbox. We'll generate our code again, and here then we can see inside the loop, as well as computing the transfer entropy estimates, we now get a computation of the null distribution there that we can get the p-values from. Let's run that code again in Octave, and this time, instead of just seeing a transfer entropy value, we will see the p-value as the measure of statistical significance of the results. Okay, so now we see we've got not only our transfer entropy between all pairs here, but we've got our p-values. Okay, we've got our p-values. Using those, we can get a much more clear idea of what's significant and what's not. So we see here that there seems to be a statistically significant between variables 1 to variable 3. There seems to be a statistically significant relationship from variable 2 to variable 4. And there also seems to be a statistically significant relationship from variable 2 to variable 1. Now, we didn't pick that before when we were just talking about the raw values themselves, but this one appears to be larger than the null distribution. Now, it's possible that that could be a spurious result. We need to remember that we're in comparing to a p-value of 0.05, 5% of the results that we test will come through spuriously. And we'll talk about what that means in particular when we're doing multiple statistical tests in the next few slides. Okay, so let me make some comments on what I've called the standard approach here to using pairwise transfer entropy to infer effective network structure. As I just said, we need to think about correcting for multiple comparisons. Using a threshold of 0.05 is sensible when we're only making one statistical test. But when we're starting to talk about network structure, we're typically making a lot of different statistical tests. When we make a lot of statistical tests, then that 0.05 chance applies to every test. If we make 100 tests, then we might expect maybe 5 of those to come up as false positives just by chance. So typically what we need to do is to drop our statistical threshold in use for each test to keep the meaning of the p-value at our system-wide level. What I mean is, instead of having a 5% chance for a single test to come up as a false positive, we want to keep our meaning of our 5% chance of getting a false positive, but have that as a 5% chance for the system as a whole. Okay, to do that, we can use family-wise error rates or false discovery rates. The simple Bonferroni correction tells us that we could drop our statistical threshold alpha, that's our 0.05 level here, by a factor of m, where m is the number of tests we make. Now, if our network is of size g, then normally we're making g times g minus 1 statistical tests here. So we have to drop our statistical threshold by a very large factor. Okay, that is a quite tough correction to beat. Okay, we need to bear that in mind, and we'll talk later in our next session about some potential other ways to address that. But importantly, we do need to think about how we correct for multiple comparisons here. We also need to properly set our transfer entropy parameters. If we don't, then we can get false positives or negatives fairly easily. What's very important here is to set our embeddings right, particularly for the target. That's something that Vibral and all showed very clearly in some simple synthetic examples. We also need to set our source target delay correctly. In what we've done so far, we've kind of assumed that there was a one time step delay between the source and the target, but that may not necessarily be the case. And often we'll scan our source target relationship over a certain range of time steps. And of course, doing that, we need to remember, is going to lead to more comparisons again. So we need to incorporate that in the corrections for multiple comparisons that we make later. Finally, we must understand that this pairwise approach doesn't address redundancies or synergies properly between sources. Looking at some brief examples here, we already talked about common driver effects and cascade effects. How if we just use pairwise transfer entropy, we may see a relationship directed between x and y here when it's really only z driving the two, or we may pick up a pairwise relationship from y to x when the relationship is really conveyed by our intermediary variable z. We'll also not necessarily pick up synergies between sources. Over on the right here in this diagram, y and z both drive x. If they were driving x in a synergistic way only, for example, if x is producing an exclusive OR outcome from the values of y and z, then we typically don't see any pairwise effect from y on x or z on x. We can only see their effects if we look at them together. So the pairwise transfer entropy approach doesn't handle the redundancies or the synergies properly. In our next short video, we'll look at extending the algorithm in a way that will handle those redundancies and synergies properly.